In nuclear physics, the semi-empirical mass formula, SEMF, sometimes also called Weizsäcker's formula, or the Bethe-Weizsäcker formula, or the Bethe-Weizsäcker mass formula to distinguish it from the Bethe-Weizsäcker process, is used to approximate the mass and various other properties of an atomic nucleus from its number of protons and neutrons. As the name suggests, it is based partly on theory and partly on empirical measurements. The theory is based on the liquid drop model proposed by George Gamow, which can account for most of the terms in the formula and gives rough estimates for the values of the coefficients. It was first formulated in 1935 by German physicist Carl Friedrich von Weizsäcker, and although refinements have been made to the coefficients over the years, the structure of the formula remains the same today. The SEMF gives a good approximation for atomic masses and several other effects, but does not explain the appearance of magic numbers of protons and neutrons, and the extra binding energy and measure of stability that are associated with these numbers of nucleons. The liquid drop model and its analysis. The liquid drop model in nuclear physics treats the nucleus as a drop of incompressible nuclear fluid of very high density. It was first proposed by George Gamow and then developed by Niels Bohr and John Archibald Wheeler. The nucleus is made of nucleons, protons and neutrons, which are held together by the nuclear force, a residual effect of the strong force. This is very similar to the structure of spherical liquid drop made of microscopic molecules. This is a crude model that does not explain all the properties of the nucleus, but does explain the spherical shape of most nuclei. It also helps to predict the nuclear binding energy and to assess how much is available for consumption. Mathematical analysis of the theory delivers an equation which attempts to predict the binding energy of a nucleus in terms of the numbers of protons and neutrons it contains. This equation has 5 terms on its right-hand side. These correspond to the cohesive binding of all the nucleons by the nuclear force, a surface energy term, the electrostatic, Coulomb, mutual repulsion of the protons, an asymmetry term, derivable from the protons and neutrons occupying independent quantum momentum states, and a pairing term, partly derivable from the protons and neutrons occupying independent quantum spin states. If we consider the sum of the following 5 types of energies, then the picture of a nucleus as a drop of incompressible liquid roughly accounts for the observed variation of binding energy of the nucleus. Volume energy. When an assembly of nucleons of the same size is packed together into the smallest volume, each interior nucleon has a certain number of other nucleons in contact with it. So, this nuclear energy is proportional to the volume. Surface energy. A nucleon at the surface of a nucleus interacts with fewer other nucleons than one in the interior of the nucleus, and hence its binding energy is less. This surface energy term takes that into account and is therefore negative and is proportional to the surface area. Coulomb energy. The electric repulsion between each pair of protons in a nucleus contributes toward decreasing its binding energy. Asymmetry energy, also called Pauli energy, an energy associated with the Pauli exclusion principle. Were it not for the Coulomb energy, the most stable form of nuclear matter would have the same number of neutrons as protons, since unequal numbers of neutrons and protons imply filling higher energy levels for one type of particle, while leaving lower energy levels vacant for the other type. Pairing energy. An energy which is a correction term that arises from the tendency of proton pairs and neutron pairs to occur. An even number of particles is more stable than an odd number. The formula. In the following formulae, let A be the total number of nucleons, Z the number of protons, and N the number of neutrons, so that A equals Z plus N. The mass of an atomic nucleus is given by m equals Z m p plus n m n minus e b c 2. Display style m equals Z m underscore p plus n m underscore n frac e underscore b c caret 2, where m p display style m underscore p and m n display style m underscore n are the rest mass of a proton and a neutron, respectively, and e b display style e underscore b is the binding energy of the nucleus. The semi-empirical mass formula states that the binding energy will take the following form: E B equals A V A minus A S A 2 / 3 minus A C Z 2 A 1 / 3 minus A minus 2 Z 2 A plus or minus delta A Z. Display style E underscore B equals A underscore V A underscore S A caret 2/3 A underscore C frac Z caret 2 A caret 1/3 A underscore A frac A 2 Z caret 2 A PM delta A Z. Closing curly bracket. Each of the terms in this formula has a theoretical basis, as will be explained below. The coefficients A, V, display style A underscore V, A, S, display style A underscore S, A, C, display style A underscore C, A, display style A underscore A, and a coefficient that appears in the formula for delta A, Z, display style delta A, Z, closing curly bracket, are determined empirically. Terms. Volume term. The term A, V, A, display style A underscore V, A, is known as the volume term. The volume of the nucleus is proportional to A, so this term is proportional to the volume. Hence the name. The basis for this term is the strong nuclear force. The strong force affects both protons and neutrons. And as expected, this term is independent of Z, because the number of pairs that can be taken from A particles is A minus 1, 2, display style frac A1, 2. One might expect a term proportional to A2, display style A caret 2. However, the strong force has a very limited range, and a given nucleon may only interact strongly with its nearest neighbors and next nearest neighbors. Therefore, the number of pairs of particles that actually interact is roughly proportional to A, giving the volume term its form. The coefficient A, V, display style A underscore V, is smaller than the binding energy of the nucleons to their neighbors. E, B, display style E underscore B, which is of order of 40 MeV. This is because the larger the number of nucleons in the nucleus, the larger their kinetic energy is, due to the Pauli exclusion principle. If one treats the nucleus as a Fermi ball of A, display style A, nucleons, with equal numbers of protons and neutrons, then the total kinetic energy is 3, 5, A, epsilon, F, display style 3 over 5 A, for epsilon underscore F, with epsilon, F, display style for epsilon underscore F, the Fermi energy which is estimated as 28 MeV. Thus the expected value of A, V, display style A underscore V, in this model is E, B, minus 3, 5, epsilon, F, 17, M, E, V, display style E underscore B 3 over 5 for epsilon underscore F Sim 17 Mathroom MEV. Not far from the measured value. Surface term. The term A S A 2 slash 3 display style A underscore S A caret 2/3 is known as the surface term. This term, also based on the strong force, is a correction to the volume term. The volume term suggests that each nucleon interacts with a constant number of nucleons, independent of A. While this is very nearly true for nucleons deep within the nucleus, those nucleons on the surface of the nucleus have fewer nearest neighbors, justifying this correction. This can also be thought of as a surface tension term. And indeed a similar mechanism creates surface tension in liquids. If the volume of the nucleus is proportional to A, then the radius should be proportional to A 1/3 display style A caret 1/3 and the surface area to A 2/3 display style A caret 2/3. This explains why the surface term is proportional to A 2/3 display style A caret 2/3. It can also be deduced that A S display style A underscore S should have a similar order of magnitude as A V display style A underscore V Coulomb term. The term A C Z Z minus 1 A 1/3 display style A underscore C frac Z Z1 a caret 1/3 or A C Z 2 A 1/3 display style A underscore C frac Z caret 2 a caret 1/3 is known as the Coulomb or electrostatic term. The basis for this term is the electrostatic repulsion between protons. To a very rough approximation, the nucleus can be considered a sphere of uniform charge density. The potential energy of such a charge distribution can be shown to be E equals 3.514 pi epsilon 0 q 2 r. Display style E equals frac 3 5 left frac 1 4 pi for epsilon underscore 0 right frac q caret 2 r, where q is the total charge and r is the radius of the sphere. Identifying q with z e display styles A and noting as above that the radius is proportional to A 1/3 display style A caret 1/3, we get close to the form of the Coulomb term. However, because electrostatic repulsion will only exist for more than one proton, Z2 display style Z caret 2 becomes Z minus 1 display style Z Z1 closing curly bracket. The value of A C display style A underscore C can be approximately calculated using the equation above. Empirical nuclear radius R approximately equals R 0 A 1 3 display style R approx R underscore 0 a caret frac 1 3 closing curly bracket. Quantum charge integers Q equals Z E display style Q equals Z Z2 approximately equals Z minus 1 display style Z caret 2 approx Z Z1 backslash closing curly bracket. Integration by substitution E equals 3.514 pi epsilon 0 q 2 r equals 3.514 pi epsilon 0 z e 2 r 0 a 1 3 equals 3 e 2 z 2 20 pi epsilon 0 r 0 a 1 3 approximately equals 3 e 2 z z minus 1 20 pi epsilon 0 r 0 a 1 3 equals a c z z minus 1 a 1 slash 3 display style equals frac 3 5 left frac 1 4 pi for epsilon underscore 0 right frac q caret 2 r equals frac 3 5 left frac 1 4 pi for epsilon underscore 0 right frac z caret 2 r underscore 0 a caret frac 1 3 equals frac 3 caret 2 z caret 2 20 pi for epsilon underscore 0 r underscore 0 a caret frac 1 3 approx frac 3 caret 2 z z1 20 pi for epsilon underscore 0 r underscore 0 a caret frac 1 3 equals a underscore c frac z z1 a caret 1/3 potential energy of charge distribution E equals 3 e 2 z z minus 1 20 pi epsilon 0 r 0 a 1 3 display style equals frac 3 caret 2 z z1 20 pi for epsilon underscore 0 r underscore 0 a caret frac 1 3 electrostatic Coulomb constant a c equals 3 e 2 20 pi epsilon 0 r 0 display style a underscore c equals frac 3 caret 2 20 pi for epsilon underscore 0 r underscore 0 the value of a c display style a underscore c using the fine structure constant a c equals 3 5 c alpha r 0 equals 3 5 r p r 0 alpha m p c 2 display style a underscore c equals frac 3 5 left frac hbarc alpha r underscore 0 right equals frac 3 5 left frac r underscore p r underscore 0 right alpha m underscore p c caret 2 where alpha display style alpha is the fine structure constant and r 0 a 1 slash 3 display style r underscore 0 a caret 1/3 is the radius of a nucleus giving r 0 display style r underscore 0 to be approximately 1.25 femtometers. R p display style r underscore p is the proton Compton radius and m p display style m underscore p the proton mass. This gives a c display style a underscore c an approximate theoretical value of 0.691 MeV. Not far from the measured value. A c equals 0.691 MeV. Display style a underscore c equals 0.691 text MeV. Asymmetry term. The term a minus 2 z 2 a display style a underscore a frac a2z caret 2a or 4a slash 2 minus z 2a display style for a underscore a frac a 2 z caret 2 a is known as the asymmetry term. Note that as a equals n plus z, display style a equals n plus z, the parenthesized expression can be rewritten as n minus z, display style nz, closing curly bracket. The form a minus 2 z, display style a2z, closing curly bracket, is used to keep the dependence on a explicit, as it will be important for a number of uses of the formula. The theoretical justification for this term is more complex. The Pauli exclusion principle states that no two identical fermions can occupy exactly the same quantum state in an atom at a given energy level. There are only finitely many quantum states available for particles. What this means in the nucleus is that as more particles are added, these particles must occupy higher energy levels, increasing the total energy of the nucleus, and decreasing the binding energy. Note that this effect is not based on any of the fundamental forces, gravitational, electromagnetic, etc. Only the Pauli exclusion principle. Protons and neutrons, being distinct types of particles, occupy different quantum states. One can think of two different pools of states, one for protons and one for neutrons. Now, for example, if there are significantly more neutrons than protons in a nucleus, some of the neutrons will be higher in energy than the available states in the proton pool. If we could move some particles from the neutron pool to the proton pool, in other words, change some neutrons into protons, we would significantly decrease the energy. The imbalance between the number of protons and neutrons causes the energy to be higher than it needs to be for a given number of nucleons. This is the basis for the asymmetry term. The actual form of the asymmetry term can again be derived by modeling the nucleus as a Fermi ball of protons and neutrons. Its total kinetic energy is E(k) equals 3, 5, n, p, epsilon, f, p, plus, n, epsilon, f, n. Display style E underscore k equals 3 over 5, n underscore p, var epsilon underscore f underscore p, plus n underscore n, var epsilon underscore f underscore n. Closing curly bracket, where n, p, display style n underscore p, n, display style n underscore n, are the numbers of protons and neutrons, and epsilon, f, p, display style, var epsilon underscore f underscore p, epsilon, f, n, display style, var epsilon underscore f underscore n, are their Fermi energies, since the latter are proportional to n, p, 2/3, display style, n underscore p, caret 2/3, and n, 2/3, display style, n underscore n, caret 2/3, respectively. One gets E, k, equals C, n, p, 5/3, plus n, 5/3, display style E underscore k equals C, n underscore p, caret 5/3, plus n underscore n, caret 5/3, closing curly bracket. For some constant C, the leading expansion in the difference n minus n p, display style n underscore underscore p, is then E, k, equals C, 2/3, n, p, plus, n, 5/3, plus, 5, 9, n, minus, n, p, 2, n, p, plus n 1 slash 3 plus o n minus n p 2. Display style E underscore K equals C over 2 caret 2/3 left. N underscore P plus N underscore N caret 5/3 plus 5 over 9. N underscore P caret 2 over N underscore P plus N underscore N caret 1/3 right. Plus O N underscore P caret 2. Closing curly bracket. At the 0th order expansion, the kinetic energy is just the Fermi energy. Epsilon F P equals epsilon F N. Display style for epsilon underscore F equivalent for epsilon underscore F underscore P equals for epsilon underscore F underscore N multiplied by 3 5 N P plus N 2 slash 3. Display style 3 over 5 N underscore P plus N underscore N caret 2/3. Thus we get E K equals 3 5 epsilon F N P plus N plus 1 3 epsilon F N minus N P 2 N P plus N plus O N minus N P 4 equals 3 5 epsilon F A plus 1 3 epsilon F A minus 2 Z 2 A plus O A minus 2 Z 4. Display style E underscore K equals 3 over 5 for epsilon underscore F N underscore P plus N underscore N plus 1 over 3 for epsilon underscore F N underscore N underscore P caret 2 over N underscore P plus N underscore N plus O N underscore P caret 4 equals 3 over 5 for epsilon underscore F A plus 1 over 3 for epsilon underscore F A2Z caret 2 over A plus O A2Z caret 4. Closing curly bracket. The first term contributes to the volume term in the semi-empirical mass formula, and the second term is minus the asymmetry term. Remember, the kinetic energy contributes to the total binding energy with a negative sign. Epsilon F display style for epsilon underscore F is 38 MeV. So calculating A display style A underscore A from the equation above, we get only half the measured value. The discrepancy is explained by our model not being accurate. Nucleons in fact interact with each other, and are not spread evenly across the nucleus. For example, in the shell model, a proton and a neutron with overlapping wave functions will have a greater strong interaction between them and stronger binding energy. This makes it energetically favorable, i.e., having lower energy, for protons and neutrons to have the same quantum numbers other than isospin, and thus increase the energy cost of asymmetry between them. One can also understand the asymmetry term intuitively as follows. It should be dependent on the absolute difference. Pipe n minus z pipe display style nz, and the form a minus 2 z 2 display style a2z caret 2 is simple and differentiable, which is important for certain applications of the formula. In addition, small differences between Z and N do not have a high energy cost. The A in the denominator reflects the fact that a given difference pipe n minus z pipe (nz) is less significant for larger values of a pairing term. The term delta a z delta a z closing curly bracket is known as the pairing term, possibly also known as the pairwise interaction. This term captures the effect of spin coupling. It is given by delta a z equals opening curly bracket plus delta 0 z n even 0 a odd minus delta 0 z n odd a even delta a z equals begin cases plus delta underscore 0 and z n text even a text even 0 and a text odd delta underscore 0 and z n text odd a text even end cases where delta 0 delta underscore 0 is found empirically to have a value of about 1000 keV, slowly decreasing with mass number A. The dependence on mass number is commonly parametrized as delta 0 equals a p a k p delta underscore 0 equals frac a underscore p a caret k underscore p closing curly bracket. The value of the exponent Kp is determined from experimental binding energy data. In the past its value was often assumed to be -3/4, but modern experimental data indicate that a value of -1/2 is nearer the mark. Delta 0 equals a p a 1/2 delta underscore 0 equals frac a underscore p a caret 1/2, or delta 0 equals a p single quote a 3/4 delta underscore 0 equals frac a underscore p prime a caret 3/4. Due to the Pauli exclusion principle, the nucleus would have a lower energy if the number of protons with spin up were equal to the number of protons with spin down. This is also true for neutrons. Only if both Z and N are even can both protons and neutrons have equal numbers of spin up and spin down particles. This is a similar effect to the asymmetry term. The factor A minus K P a caret K underscore P is not easily explained theoretically. The Fermi ball calculation we have used above, based on the liquid drop model but neglecting interactions, will give an A minus 1 a caret minus 1 dependence, as in the asymmetry term. This means that the actual effect for large nuclei will be larger than expected by that model. This should be explained by the interactions between nucleons. For example, in the shell model, two protons with the same quantum numbers, other than spin, will have completely overlapping wave functions and will thus have greater strong interaction between them and stronger binding energy. This makes it energetically favorable, i.e., having lower energy, for protons to pair in pairs of opposite spin. The same is true for neutrons. Calculating the coefficients. The coefficients are calculated by fitting two experimentally measured masses of nuclei. Their values can vary depending on how they are fitted to the data. Several examples are as shown below. With units of megaelectron volts, the semi-empirical mass formula provides a good fit to heavier nuclei, and a poor fit to very light nuclei, especially for He. This is because the formula does not consider the internal shell structure of the nucleus. For light nuclei, it is usually better to use a model that takes this structure into account. Examples for consequences of the formula. By maximizing ebb A, Z. With respect to Z, we find the best neutrons to protons ratio N, Z for a given atomic weight A. We get N/Z approximately equals 1 plus A, C, 2, A, 2 slash 3. Display style N, Z, approx 1 plus, frac, A underscore, C, 2 A underscore, A caret, 2/3. Closing curly bracket. This is roughly 1 for light nuclei. But for heavy nuclei the ratio grows in good agreement with nature. By substituting the above value of Z back into ebb, one obtains the binding energy as a function of the atomic weight, ebb A. Maximizing ebb A with respect to A gives the nucleus which is most strongly bound, i.e., most stable. The value we get is A equals 63. Copper, close to the measured values of A equals 62. Nickel, and A equals 58. Iron. Notes. Friedman, R. Young, H. 2004. Sears and Zimanski's University Physics with Modern Physics. 11th ed. pp. 1633–1634. ISBN 0-8053-8768-4. Liverhunt, S. E. 1960. Elementary Introduction to Nuclear Reactor Physics. John Wiley & Sons. pp. 58–62. LCCN 60011725. Chopin, G. Lil Jensen, J. O. Rydberg, J. 2002. Nuclear Mass and Stability. PDF. Radiochemistry and Nuclear Chemistry. 3rd ed. Butterworth Heinemann. pp. 41–57. ISBN 978-0-7506-7463-8. The Semi-empirical Mass Formula. Nuclear Liquid Drop Model in the Hyperphysics Online reference at Georgia State University. Liquid drop model with parameter fit from first observations of excited states in the neutron deficient nuclei 160161W and 159 tar. Alex Keenan, Ph.D. thesis, University of Liverpool, 1999. HTML version.